Okay, so this is work that we did at Sprint Labs in collaboration with SprintLink Engineering and Dave Meyer. I'll start off with a statement about what problem we're trying to address, what questions we're trying to solve, what questions we're trying to answer, and then go into a methodology of how we collect our routing data and our packet data, and how we analyze it to answer our questions. And then I'll present our results and try to explain why we see those results, and then end with implications of our findings. There's been a fair amount of prior work that's looked at the growth of routing tables and the growth in the number of BGP updates. There's the work by Jeff Houston and Olaf Manel, and also the work by Cowie that showed the impact of the NIMDA worm on BGP updates. The concern here is that excessive BGP updates can cause routing and traffic instability. This is especially troubling when you get Leibowitz's work on showing how slow inter-AS routing convergence can be. If there are a lot of BGP updates, then the issue is that routes may keep flapping and addresses may become unreachable for short periods of time, and that can affect traffic stability. However, within a single AS, BGP updates can also be a concern. If a lot of BGP updates are being received at an autonomous system, then those BGP updates will cause a certain amount of protocol traffic. Each BGP update will take up a packet, but I really don't think that's a huge concern. But another concern is that it may increase the router CPU utilization. Also, every time a BGP update is heard at a large AS, the intra-domain routes may also be affected. The exit point for a particular router, for a particular destination address, may change for a large AS, and that can cause route reconvergence and eventually also lead to shift in traffic. It's this last issue that we're concerned with, and I'll now go into an example of how this can happen. So this is a toy example of, consider the Sprint backbone in the middle, where I'm showing 3 POPs, and we've got some customer AS that connects to us at POP B and at POP C. And let's say that for now the BGP announcements have been set up such that traffic going to this customer will exit the Sprint backbone for every trace. Now, the goal of our work is to try and identify the traffic variability that is caused by BGP updates. And this ingress link to multiple egress fanout will reflect that variability and the variability due to that's already present in the traffic itself. So we do this calculation twice. We first do this calculation with a static BGP table that we apply to the whole trace. And then we get one ingress link to multiple egress POP fanout. And then we again do this calculation using a dynamic BGP table. That is a BGP table that we continually update, and we correlate the data packets along the length of the trace. And now we've got 2 sets of ingress link to egress POP fanouts. One shows the variability inherent in the traffic. The other shows the variability that's both inherent in the traffic and is caused by BGP updates. We subtract these 2, and then as a result, we get the variability that's due to the BGP updates. Now I'll present our results and try to explain why we see them. I'll be presenting results from one particular packet trace that was 22 hours long that we collected on August 6th of last year. The average link utilization was about 112 megabits per second. We did look at 5 other packet traces as well, and the results are similar. We've made two main approximations here. One main approximation that we made is that we calculate the BGP table in the dynamic BGP case every 20 minutes. The reason for that is this particular packet trace has about 2 billion, a lot of packets, and And basically, by calculating the BGP table every 20 minutes, we get to aggregate all of the packets into a set of destination addresses. So if there were 50 packets to a destination address, we only need to look up that one destination address once instead of 50 times. We've done this calculation for small sections of the trace for finer time granularities, and we see no difference in our results. The other approximation that we make is that we only consider 99% of the traffic. The reason for that is out of the 200,000 destination addresses in this 22-hour packet trace, only 30,000 of these destination addresses account for 99% of the traffic. So that saves us a lot in computation time. I'll start with a graph of the BGP updates that we see. The first graph shows the number of iBGP updates that we see during a week around the trace collection time. Now, this is from the Zebra software speaker that connects to this router. So over here, we're actually showing the number of changes to the routing table itself. Along the y-axis, we show the number of BGP events clumped up into 20-minute bins. And we see that there's a continuous noise of about 133 updates every minute. And we see that there are periods of spikes where the total number of updates can go as high as 9,000 updates per minute. We think that these spikes may be due to maintenance windows of various ISPs. They tend to happen around Saturday or Sunday. We've also made graphs of BGP updates over a whole month, and we see similar patterns. The second graph here is a histogram of the number of BGP updates. And we see that along the x-axis is the number of updates, along the y-axis is the histogram. And we see that the average of 133 every minute, this is in a 10-minute bin, is fairly common. And the outliers of thousands of updates per minute are relatively rare. So these are graphs for the amount of traffic that went from this particular ingress link that we measured to a particular egress POP. And we have this same set of graphs for all of the egress POPs in the Sprint backbone. Now, this top graph shows along the x-axis the time along the trace from the beginning to the end of 22 hours. And along the y-axis is the number of bytes. And over here, it goes between 100 megabytes to 200 megabytes. Oops. And we see that there are two lines on top of each other here. The red line shows the number of bytes that went from this ingress link to this egress POP when using a BGP table that was continuously updated. And the green line shows the number of bytes that went from this ingress link to this egress POP when we were using a fixed BGP table across the length of the trace. We see that there is a lot of variability that's inherent in the traffic itself here, and the two lines are on top of each other. So when we subtract out the two lines, we get the second graph, which shows the difference between the two graphs. And so if there's a positive value on the second graph, that indicates that more traffic went to this particular egress POP as a result of a BGP change. Or if the graph is negative, it shows that less traffic went to this egress POP as a result of a BGP change. We see that the y-axis scale on the second graph is about 5 megabytes. And we compare that to the 200 megabytes on the first graph, we see that the variability is only about 1 to 3%. And this graph is representative of all the other egress POPs for this particular ingress trace and is representative of the 5 other ingress traces that we also looked at. So even though this is a very small amount of variability, we have looked at what's been causing this variability. And we've noticed that in all cases, networks, destination networks with multiple links or paths to the Sprint backbone have been involved. We found that BGP updates cause shift between these inter-AS paths, and because the inter-AS path shifts, and because these inter-AS paths connect to Sprint at different egress POPs, there is shift in traffic inside the Sprint backbone. Here are two common examples of what happens. Here's a Sprint backbone, and we've got a particular customer that connects to us at POP 1 and at POP 2, and BGP updates will cause traffic to shift between this link and this other link. Or the other common scenario is where we've got a customer that connects to us directly in a particular POP and then connects to us indirectly through a peer to another POP, and then BGP updates will cause traffic to shift both from a shorter path to a longer path and from a longer path to a shorter path. We've also found that in most of the variability, which is only 1 to 3%, we found a single next hop was involved in 47% of all the traffic shifts. We also found that of all the traffic shifts, 46% of all the traffic shifts, a single destination or origin AS was involved. However, we didn't find the case that egress POP shifts happen rapidly throughout the length of the trace. We noticed that an egress POP shift would happen only a few times at most for a particular destination address. But this is for only 1% of the traffic. Why is the other traffic stable? For that, we look at the characteristics of this traffic. We've noticed that of all the traffic measurements that we've done, heavy hitters have been present. By that I mean for 100% of the traffic on this ingress link, we have about 200,000 destination addresses. But for 99% of this traffic, only 15% of those destination addresses are involved. And for 80% of the traffic, only 1.5% of those destination addresses are involved. So what we want to look at now is which of the BGP updates affect these heavy hitters, because they account for most of the traffic. And then of these updates, which of them cause a change in the egress POP for these destination addresses. This top graph shows the number of iBGP updates, or the number of changes to the iBGP routing table during the length of the whole trace. And again, we see the constant noise of about 100 updates per minute, and we occasionally see some spikes going up to about a couple of thousand updates per minute. Now, the second graph shows the number of BGP updates for only the heavy hitters, or the destination addresses that account for 80% of the traffic. And we see that we're talking about far fewer updates now. We're talking about 5 to 15 updates. Now, I was just showing you all of the BGP updates. Not all of the BGP updates change the next hop. If the next hop changes, then the egress POP can change. So in this top graph, I'm showing you all of the next hop changes for all of the destination addresses, for all of the destination addresses in a BGP table. We see that there's still a fair amount of constant noise, but then in the second graph, we are now looking at the number of next hop changes only for the heavy hitters, which is 80% of the traffic. And we see that the number is far lower. So there are 2 points here. One is that even though there are so many BGP updates, relatively few of them matter for this particular problem. And secondly, I also want to point out that the heavy hitters don't change much in their next hop. The average number of next hop changes for any prefix was about 0.63 during the length of the trace. And for the heavy hitters, the average number of next hop changes was 0.1. So the conclusion is that BGP updates hardly affect intra-Sprint traffic fan-out. And this is consistent with prior work from Jennifer Rexford, who did measurements of the AT&T backbone and found that the heavy hitters tend to have stable prefixes. Why is this? Maybe standard BGP route filtering is doing a good job. Maybe it's the case that only stable prefixes can track stable traffic. Or it could be that layer 3 protection switching and engineering is doing a good job of keeping backbone traffic stable. But there are so many other BGP updates. What is causing them? To answer some of these questions, we would have to determine where BGP updates come from and what's causing them, and we would have to snoop BGP sessions all across the world to figure that out. So the implications of our work are that BGP doesn't cause latency variation within the Sprint network, which is good for certain applications such as voice over IP. And also, BGP doesn't make link loads more dynamic within the network. And that makes traffic engineering and provisioning easier because the traffic matrix is now less stable. It is less variable. It is still unstable due to inherent variations in the traffic, but you don't have to worry about the variations from BGP itself. And lastly, I'd like to point out the website for our group. It's got data from the analysis of various packet traces and routing data on there, as well as a bunch of research papers and contact information for us. Thank you.
Hi. Nice talk, by the way.
Thanks.
What percentage of your customers and peers actually pass you MEDs?
I'm sorry, I didn't catch the last part.
What percentage of your customers and peers pass you MEDs, MEDs?
Oh. It's a good question. I don't have that number.
Actually, it would be nice to split the work to ones who are passing MEDs versus not passing MEDs and see if there's actually a difference. I think that would be a nice addition. The other thing is actually especially for the part that the MEDs are not passed, IGP type tracking is used to figure out which pub to exit. Did you simultaneously also look at the IGP messages and see if that's actually affecting that's actually causing a change of the exit pub?
Oh, so when we look at the iBGP table itself, we are any IGP changes are reflected in that table. So we are accounting for that. But then, since we hardly see any variability, we didn't actually bother to figure out whether IGP was causing the small amount of variability that we saw.
Okay, thank you.
Your data was taken during one period, or did you look at multiple periods where you might be losing connectivity to a peer or having an exit peer?
We collected data across 3 different days, and connected to 6 different ASs. So that's the extent of our data.
Okay. During any of those times, did you have any flapping of connectivity either to the exit peers or to the next hop for the BGP?
When we collected those packet traces, we didn't notice any major outages at all. But any specific ones, such as excessive BGP updates, they would show up in the BGP updates itself that we collect, and that would get reflected in our analysis.
So let me make sure I've understood it, because this is a point where people have asked problems. Have you seen the connectivity to the exit gateway or to the BGP peer go on and off repeatedly in any of your samples, and are you planning to look for that particular problem?
So I think you're asking me if there were any IGP failures or any failures within the Sprint network during...
Either failures within the Sprint network to the exit gateway or failures to the remote AS's peer.
Well, I didn't actually try to correlate whether there were failures within the network or from the network to the rest, other than what would have already been seen in the BGP updates.
Okay, that might be interesting along with Cengiz's comment. And by the way, it is a good talk. Thank you very much.
Thanks.
I have one question myself. So it's along the same lines, and I guess given the other questions, it's maybe not as specific as it could be, but I'm interested in any other observations you might have. I guess if the summary is that when traffic is stable and everything is working, then the network works well, I guess that's a good result. And I think this is, it's useful to see that actually with some analysis. But along the lines of the other comments, if we had more insight into what's happening when something's broken, and whether, as we talked before, if those periods where you had a higher rate of instability, if any analysis was done during those periods, and if you saw anything different other than during the kind of steady state background noise BGP.
Right, so the worst number of updates that we saw were about 9,000 updates per minute, and that was usually during the weekends, and we think that was during maintenance cycles of various ISPs. During the length of of the various traces that we collected, the worst that we saw was about 2,000 updates per minute. And so we haven't actually collected any or haven't analyzed any data during the weekends to see if those maintenance cycles could actually affect this issue.
And it doesn't look like there are any other questions. So thanks again very much. I think this is good work, and I appreciate you sharing it with us.